Hello, I'm Anna Mackay and today we're looking at exponential functions. So the question we've got here is, how do we evaluate a to the power of n when n is a real number but it's not necessarily rational? To answer this question we need to study the graphs of exponential functions. So thinking back to some of the things we've done, say 2 to the power of 2, a base number, so again 2 to the power of 3. We've been dealing with integers and whole numbers. What if it's to the power of 2 to the power of pi, or 2 to the power of the square root of 7? If we can look at the graphs of these functions, then we'll be able to work out the answers to those things. And so the most simple exponential function is of this form: base a to the power of x, where a is greater than 0 but not equal to 1. So traditionally you've dealt with linear functions, quadratic functions, where it's x to the power of something. This time round, for exponential functions, x is in the power. It is the exponent. So this function here, y equals 2 to the power of x, thinking about what its graph might look like if we were to think about a table of values. So what we're going to look at is, for each value of x, what will the value of y take? So that's where you substitute in all of these different values. For example, 2 to the power of 2, the answer down here should be 4. Let's have a look at that, and it is. So here's all the ones for positive powers and negative powers. What do you notice about the answers here for y? That they're all greater than 0. So even when you substitute in negative numbers as the power, you'll remember from your work with index laws that, for example, to the power of negative 3, the answer is 1 over 2 to the power of 3, which is the same as 1 over 8. So all of these answers, the y values, are positive numbers, and therefore the graph of that looks like this. So all the y's are positive, so that's all in the positive y region, and we've plotted all the other points. Having a look at what happens for the positive powers, how that changes dramatically, and for the negative powers, you still have positive y values, but I guess the distance vertically between them is getting smaller and smaller. So that's what we're talking about, that when x heads towards negative infinity, so the x values head all the way out to the left here, heading towards negative infinity, the y values are getting closer and closer to 0, but always from above. And that's what that positive sign means. We say y approaches 0 from above. Because if you look what's happening here, you're having 1 divided by 2, 1 divided by 4, 1 divided by 8. So it's 1 divided by increasingly bigger numbers, and each of those values get closer and closer to 0, but they're always greater than 0. And we describe this graph as asymptotic to the x-axis. So if you're asked to describe the behaviour of an exponential function, it's asymptotic, in this case to the x-axis, but it can be to other horizontal lines. In this case, the horizontal line that it's asymptotic to is y equals 0, and that's called a horizontal asymptote. Some facts here: there's an investigation in the textbook that I encourage you to do, and here's the summary of the results that you would find from that. I'm not going to go through these at this point. Jot them down in your notebook. Just in the summary though, that B controls the vertical translation, so of that graph that we looked at just before, a basic exponential there, how much it can be vertically translated up or down. C is a horizontal translation. A controls how steeply the graph increases or decreases. And the horizontal asymptote is y equals b. So it's the number that's added or subtracted on at the end. Think back to that last graph, 2 to the power of x. There was no number added on, well technically it was add 0, and that was the horizontal asymptote. Y is equal to 0. So if you're asked to sketch this graph, y is equal to 2 to the power of negative x take 3. Now we're going to assume you're not using your calculators here. How do you do that? My suggestion is create some points. You could do a whole table of values if you like, but let's just do a few points here. Intercepts are often a handy one to do. We'll come back to that one. We'll say what the horizontal asymptote is. Can you anticipate what it's going to be? So the horizontal asymptote is that number that's subtracted off the end. So it's negative 3, but you don't just write negative 3, it's y is equal to negative 3. That would be a horizontal line at y is equal to negative 3. I might just put that on there for you to visualise now. Next, the y-intercept, what value does x take there? takes 0. So we're going to substitute in when x is equal to 0. So we get 2 to the power of 0 take 3 equals anything to the power of 0 is 1. 1 take 3, we're at -2. So that's going to give us the point 0, -2. Perhaps I could put that on down there. Now, if you were to solve for when y is equal to 0, you don't probably have the knowledge yet on how to solve that because x is in the power, and how to get x down out of the power involves logarithms, and we'll get to that later. So instead of putting y is equal to 0, let's choose another few values for x and substitute them in. I'm going to substitute x is equal to 2 and -2. Go ahead and do that if you like, or wait for the answer. For x is equal to 2, we get our final answer there. I will write it as a mixed number this time around. We usually use improper fractions. So it's -2 3/4 on the y, and that's when x is 2. So I might put a dot there. And when x is equal to -2, the result is 1. And so that point at -2, y is +1. And so you've got a rough idea of how that graph's going to look now. So you connect the dots. Putting on arrows should label the x and y axis. I haven't got that at this second in time. And here's one that's drawn much more neatly. That's coming in a minute. On this screen, I've got all of what we've just said written out neatly with those, the y-intercept, the x values, and the domain and range. Well, while it's on this screen, let's talk about it there. Range are all the y values. So what can they take? Looking up and down the y-axis here, it looks like it's going up to infinity. And does it keep going down to -infinity? No. They're all going to be greater than a particular number, and that number is -3. And then the domain are the x values. Looking along the x-axis to the left and to the right, will it end the number of x values? It won't. Don't be fooled by the fact that you can't see the rest of the graph. You could keep substituting in x numbers in here into the negative x numbers and positive x numbers, and that graph will go on forever. So as you can see here, domain is those curly brackets. X belongs to the set of real numbers with the double line for the r, and y is greater than -3. We asked the question, could y be equal to -3? So that's where we would substitute the number of -3 in there. And so it's asking, if you were to rearrange that algebraically, you'd be getting, when is 2 to the power of -x equal to 0? Well, 2 to the power of anything can never be equal to 0, so that one doesn't exist, and that's why it's always greater than 0. Just an extra side bit, occasionally you're going to get asked questions to estimate from a graph the answer for this. You're saying, so when is this function equal to 1.5? Now notice that 1.5 is in place of the y, so we're saying, well, when is the y value 1.5? So you come along to the y-axis and you estimate where 1.5 would be, say about there, and then you go across until it hits the graph, about there, and then you look down and you see, well, what is the x number that lines up with? It's an estimation, so you would say, x is approximately equal to -2.2 or something like that. What if you had a second one here, and in place of x we have the number, well, what number have we got? Is it -1? It's not actually, because the formula has the negative there. So x is actually equal to 1. So it's asking you to estimate the answer to that. So you think, well, where is x equal to +1? You come down to the graph and see where that hits, and you're working out its y coordinate at that point. So you go across to the y-axis and read the number off there. So we'd have, say, maybe approximately 2.5, but -2.5. So that's how you do those questions. Join me in the next video for growth and decay, and where we just look at growth. Subscribe to the channel and give it a thumbs up. Thank you.